Okay, this is going to be lecture 7. This is where first time we are going to create a system of vectors, 3 vectors which are orthogonal to each other. So orthogonal basis. Now what do we mean by base? Now if we have, say, in 3-dimensional system 3 vectors which are linearly independent, then they can be the base of this 3-dimensional system. Now it is customary, it is convention is that you take 3 vectors which are mutually perpendicular to each other and the length of each vector is 1, that is unit vector. Then if this is the system that we are going to use, then this system is called system of orthogonal basis, and this is I. We call the first, which is in x direction, unit vector I, then perpendicular to that is j, and perpendicular to that is k. So this is an orthogonal base system. In 3-dimensional system we can geometrically show that there exist 3 vectors which are mutually perpendicular to each other and their distances, the lengths of these 3 vectors equals 1. However, as you increase your number of dimensions, in 2-dimensional system we can do it I and j. In 1-dimensional system we can do it I, but if the dimensions go more than 3, that is 4, 5, 6 and eventually n, then geometrically showing these mutually perpendicular unit vectors or orthogonal bases is going to be difficult, but algebraically you can always have them. So presently we are going to restrict our discussion on 3-dimensional geometry. Therefore I, j and k are the 3 orthogonal bases that we are going to have. What is so good about these orthogonal bases is each one is perpendicular to the other, therefore their dot products I dot j is equal to j dot I is equal to 0 and so on. I dot k and k dot I and j dot k and k dot j is going to be 0. What is going to be I dot I? Unit length is 1 into angle between them is 0, so cos 0 is 1, so it is going to be equal to 1. So we get the length. So any vector I, j and k, if the dot product is taken with the other one, it is going to be 0 because they are perpendicular. That is the advantage of having them mutually perpendicular. If they are not perpendicular, if it is an oblique system, then your cos theta is not going to be 0. We are exploring the definition of dot product, that there exists a cos theta in that definition, and therefore we are taking them mutually perpendicular. So how do we use this? Now this is going to be our x-axis. Eventually in 3-dimensional system this is going to be our y-axis, and unit vector along that is I, unit vector along y-axis is j, and unit vector along our z-axis is going to be k. And therefore if we take any point in space A, and if we decompose it in A1i plus A2j plus A3k, in these 3 unit vectors, if we take a linear linear combination of I, j, k, and the scalars are A1, A2, A3 to produce the vector A, that is what we learnt in previous lectures, that we can produce any vector in this 3-dimensional space using base vectors I, j and k, and if A1, A2 and A3 are the scalars, then suppose we produce one more vector which is B, looks like B1i plus B2j plus B3k, then what is going to be A dot B? What will be the scalar product A dot B? Now this is what is algebraic expression, because we have got vector A and vector B in their components. how much in the direction of x-axis, how much in the direction of y-axis, how much in the direction of z-axis. So if we take A dot B and we have proved properties of dot product that they are commutative, distributive, etc. So A1 we have to practically take dot product of RHS also, and if you observe, A1I dot B2J is going to be 0, A1I dot B3K is going to be 0, and therefore only terms which will survive is A1B1, I dot I is 1 plus A2B2 plus A3B3. So A dot B is going to be A1B1 plus A2B2 plus A3B3. Now, what will be the length of, say, vector A? Length of vector A, if we want to find out, then we should take A dot A. A dot A is going to be again A1 square plus A2 square plus A3 square. So this will be the, and we know A dot A is mod A square. So length of any vector in three-dimensional space is the square root of, or maybe square of the length is equal to the vector with its own dot product. And if we have the components with us, A1, A2, A3, then it will be something like this. Similarly, we can find out angle between vector A and B. Suppose this is vector B and this is vector A. What is the angle between vector A and B? Again, it is going to be simple, because now we know everything. Angle between cos theta was equal to A dot B upon absolute value of A into absolute value of B, and now we know A dot B is A1 B1 plus A2 B2 plus A3 B3, that goes in the numerator, and square root of A1 square plus A2 square plus A3 square gets into denominator, and similarly square root of B1 square plus B2 square plus B3 square goes into the denominator. So if this theta is going to be 0, then the numerator is going to be 0, because if they are not 0 vectors, then of course the denominator is not going to be 0, and if cos 90 is going to be 0, so if these two vectors are going to be perpendicular to each other, then the condition that we get is A1 B1 plus A2 B2 plus A3 B3 is going to be 0. So if A perpendicular B, then A dot B is equal to 0, implies this sum is going to be equal to 0. So this is important. Now let us do one problem with this understanding. Now you will find that I am just clearing this board immediately I stop speaking, but you can always pause, write down whatever is there on the board, and then start the new video. But I cannot wait so that you write it down, because otherwise we will increase the length of the video unnecessarily. So problem is, given two vectors are given to you. A is I plus j minus k, and B is I minus j plus k. Find unit vector C. Find unit vector C. Unit vector is normally denoted by cap. So find C perpendicular, find C, unit vector C, which is perpendicular to A and coplanar with A comma B. That is first problem. And second problem, also find vector D. Let us call unit vector D perpendicular to both A and C. Okay, so you try these problems, get the answers, and pause this video. Try these particular problems. See if you have understood dot product or not, and then let me show you how to do it. Maybe the first problem. First of all, you are supposed to have vector C which is perpendicular to A and coplanar with AB. So how do you get vector coplanar with AB? How do you get vector coplanar with A and B? Any vector which is coplanar with A and B is going to be linear combination of A and B. So you can take lambda times I plus j minus k plus mu times I minus j plus k is the vector which is coplanar with A and B for some values of lambda and mu. Now this vector should be perpendicular to A. We are searching for vector C, so now we have produced vector which is coplanar with A and B, and now we are supposed to make it perpendicular to A. So we should take dot product with I plus j minus k, and this dot product should be equal to 0. That is what is the whole idea. Now we have to collect the terms in this first. So lambda plus mu times I plus lambda minus mu times j plus minus lambda plus mu times k. This is what is your this vector dot I plus j minus k should be 0. Now if we take dot product, then only lambda plus mu I dot I plus lambda minus mu j dot j plus minus lambda plus mu minus lambda plus mu times minus 1 should be equal to 0. So if we evaluate this, then we get mu is equal to 3 lambda. Mu is equal to 3 lambda. So if you substitute mu is equal to 3 lambda here, then you will end up getting vector. So this is 3 lambda. So 3 lambda plus lambda I, that is 4 lambda I. Now you can take lambda out because it is going to be present everywhere. 4 lambda I. Now 3 minus 3 lambda plus lambda. So minus 2j, and 3 lambda minus lambda is plus 2k. This is going to be the vector, but this vector is not unit vector. Therefore we have to divide this vector by the length of this vector to make it unit, and therefore you will observe that we have to divide this by root 24 lambda. So lambda lambda gets cancelled, and therefore this is what is the vector that you are looking for. That is what is the answer. You may try the second one on your own. One more problem. A, B, C are mutually perpendicular and equal in magnitude. Show that A plus B plus C is equally inclined to A comma B comma C. Mutually perpendicular and equal in magnitude. So this is basically, suppose you assume a cube, or a cube has got length 1, but then a cube of any length you assume, and then what is going to be your A plus B plus C is going to be the diagonal longest, or all of them will be equal. So A plus B plus C is going to be, so let us draw quickly. Now this is your, say, vector A, vector B, vector C. Then this vertex and this vertex, these two vertices joining vector is going to be A plus B plus C. And now you have to show that this vector A plus B plus C, whatever angle it makes with A, whatever angle it makes with B, and whatever angle it makes with C, all of them are equal there. So it is simple problem. So Basically what you are supposed to use is cos theta 1, cos theta 2 and cos theta 3 and get all the things in place, considering what is going to be the length of a plus b plus c. So a plus b plus c dot a plus b plus c is going to be an important quantity. So this is initial things about orthogonal basis. Now let us move and get into finding out the equation of plane in the normal form. Okay, because now we have a dot product with us, that is the new multiplication of two vectors that we have defined. We will be able to write down the equation of a plane using dot product. So what is given now? Suppose I want to find out equation of this plane, and given is, suppose there is origin and we drop perpendicular from origin, and then this is point K and we wish to find out. So from origin, if the distance of the plane is given to be equal to P, suppose plane is P distance away from origin, this is perpendicular distance, we need to find out all the points in plane such that they are part of that plane, and the plane is P distance away from the origin, and we have been given this normal vector also, unit vector n is also given. So if we have been given a vector like this, then we can find out all the parallel planes to this particular vector, perpendicular planes to this particular vector, and if there is some origin and a distance from origin is mentioned, suppose it is say 5 and this is origin, so at distance 5 there will exist a plane which is going to be unique. Of course at distance minus 5 there will be another plane which is going to be parallel, and the distance between the origin and that plane is also going to be 5. But then if we have that sense, now n is in this direction and the distance p is also in this direction, therefore there will be a unique plane perpendicular to this vector in this three-dimensional space. So what are we going to do now? Let P be any point whose position vector be R. So this is what is R position vector. We want to find out all those R's. So basically, and we are supposed to use the dot product. So if we join this, then what is that we have with us? PK or vector KP. Vector KP is equal to OP minus OK. This we know. Vector KP is OP minus OK, and KP is going to be perpendicular. So what is OP? OP is R, and OK is P times unit vector, correct? And KP is going to be this vector KP, right? So what, we have not used dot product yet, so let us use KP, vector KP and OK. KP dot OK is going to be equal to 0 because they are perpendicular. So R minus P n cap, R is a vector, P is a scalar, into what is vector OK? P n cap is equal to 0. Is that right? And therefore, what do we have? R, this is dot product. So R P R dot n cap times P times R dot n cap. P is a scalar, R dot n cap is equal to P square n cap dot n cap is 1. N cap dot n cap is 1, and therefore we have P is a distance which is non-zero, therefore we can cancel. R dot n cap is equal to P. So this is the equation of plane when we are given a perpendicular vector and distance of that plane from origin. This is the. Now let us geometrically understand this equation. If we take any vector r, that means P is any point in this plane, just I am trying to explain you this geometrically, and if we take projection of OP, that is r vector on unit vector n, if we take projection of vector r on vector n, then it was, what is projection of vector r on vector n? It is r dot n upon absolute value of n. So, but absolute value of n is 1. Therefore, r dot n is a projection, and that projection distance, that is dot product, so it's a scalar. Now, r dot n cap unit, this is unit vector. Therefore, r dot n cap is a length of projection of every vector r on vector unit vector n. That is what is the meaning of this, and we want that distance to be P. So this is what is the geometric interpretation of equation of a plane in the normal form. Now suppose it is given, just one variation here which we should understand is, suppose I give you an equation looking like r dot n is equal to q, where n is a vector and q is a scalar, and n is not a unit vector, but this is, I can say that this is the equation of a plane perpendicular to vector n, perpendicular to vector n, but this is not having distance q from origin, because you never know, this is not unit vector. So can we consider this as an equation of plane or not? Of course yes, because now using this equation we can always go back, r dot n bar upon absolute value of n, distance of this n vector, what is the length of this vector, is equal to q upon absolute value of n. So if we divide both sides of this equation by absolute value of n, that is the length of that vector n, then this form is exactly equal to this. This is now unit vector n hat. This is unit vector, so r dot n hat, and what is the distance of origin from that plane? It is going to be whatever number q you have been given divided by length of the perpendicular vector. So you may end up having equation of plane in this form, or you may end up having equation of plane in this form. We should be comfortable with that. And if that n is a unit vector, then RHS is the distance, which is P, and if that n is not unit vector, then you can make it unit vector and get the distance. Otherwise it is the equation of plane only. Now can we do it, instead of telling you the distance from origin, if we give you one more point, let the point, this point be A. So a perpendicular vector is given and another point in space is given. We need to find out equation of plane which is containing A and perpendicular to this. So yes, of course we can do this by TKP. Now P is any point, that is R. So P R minus A is going to be the vector P. Is that right? Now what is not available with us is this distance. Okay, so maybe we will solve this problem geometrically, but perpendicular vector n is known, distance is not known, so I can always create that distance by joining OA and taking projection on n. So what is the projection of vector OA on n? Projection of vector OA on n is let us say this is A. So projection is A dot n cap. This is what is the length of the projection P. So that is what was the P in the earlier equation, A dot n cap. And now what was the RHS is going to be? Same, R dot n cap. If you take projection of any other vector on n cap, its length is equal to projection of vector A on n cap, then all those points are in the same plane. This is how you can do it. Okay, this is one way of getting the equation. Another way of getting the equation is R minus A is a vector, and that vector has to be perpendicular to n hat. So taking dot product with n hat, it should be 0. All those points P should be such that AP, vector AP should be perpendicular to n. If vector AP is perpendicular to n, that means all those r's are in the required plane. So r minus a dot n cap is equal to 0 will give us this. Geometrically, you did not have the projection or the distance from origin. So you produce the distance from origin and TKP, same formula we have used. So these are very, very important formulae as far as equation of plane is concerned, and you might require to use this. The earlier one, linear combination, also it's sometimes required, but this is more oftenly required compared to earlier. So the problem, find the equation of the plane coaxial with planes r dot n1 is equal to q and r dot n2 is equal to q2. This is, now we are developing the theory using general notation. It is not a specific plane or a line which is given to you, and this is in general happening. So coaxial, planes coaxial with given plane, planes so two planes are given to you, r dot n, r dot n1 is equal to q1 and r dot n2 is equal to q2, and we are supposed to find out equation of a plane coaxial with these two planes. That means suppose one plane is like this, another plane is like this, this is the axis which is common. So we want to find out a plane which is coaxial with this. So axis is same, coaxial means the axis is same, and passing through some point A, passing through some point A. Suppose the point A is here, its position vector is 1. So we will have to have a plane looking like this, something like this. We have to find out. Okay, and now here the u plus lambda v or s1 plus lambda s2 method is only going to work. So equation of all planes passing through, what is the equation of planes which are coaxial? Equations of plane r dot n1 minus q1 plus k times r dot n2 minus q2 is equal to 0. For different values of k, we will get different planes. Now this is the equation of family of planes which are coaxial. Now this might be little difficult at this stage because we have learned two-dimensional geometry and s plus lambda l or s1 plus lambda s2 or u plus lambda v. Those things we have done last, June, July or something like that. But now if we are dealing with say higher mathematics, now we are dealing with vectors, there is no other way for finding out all the planes which are coaxial with given two planes. This is the only method. Now I am writing it like this and saying that all planes passing through this axis, but I should have written k1 and k2 here, so that if you want one of the two planes to survive by taking the other value 0, we will get it. But now let us not make it still complicated. Anyway, we are developing the theory. Therefore, I take first plane here and second plane here with k as my parameter for different values of k. I will keep getting different planes, and therefore now if the plane has to pass through given point A, let us just simplify this. This is going to be equal to r dot n1 plus k into is equal to q1 plus kq2. This is what is the same equation, and line of intersection of this to find k. Now if we find the value of k for this A, then our job will be over. So for finding out the value of k, we should substitute, instead of r, we should substitute point A. So for finding out k is present here as well as here. Therefore A dot n1 plus k into is equal to q1 plus kq2. So k comes out to be equal to A dot n1 minus q1 upon q2 minus A dot n2. So if you write this k back over here, that is what is the plane passing through A and coaxial with given two planes. Understood? Now I am going to stop this video now, because you need to go through it couple of times and understand what we have done. Once understood, you can look at the second video. Okay, thank you.